people seem to enjoy the fact that I said that we don't know everything about what we do, and that there's a lot of open questions. So the whole point of this talk is to let you know that we don't know anything about it. It's really to show you something that we are constantly looking for or trying to study. And it's a wild guess that I've been having over the last 5 years. My students are tired of hearing me say this, but I haven't put money on this. I haven't put money, but people are telling me that I should. But in the next decade or so, there will be one Nobel laureate that will win the Nobel through stuff that you're gonna hear today. I'm very much convinced that it won't be me. I'm working on a mission that hopefully will lead to that person getting the Nobel, but I'm not the leader of the mission, so I'll be just a pawn into pushing or helping, aiding that person to get the Nobel. So for me, again, thank you very much for having me. I really enjoy. I really look forward to this event, even though every year I have to come up with something different. But it's funny because first of all, last year I had my phone with me and I was on call because my wife was due that day. So happy to report that. So that was born. His birthday is going to be in 4 days, so on the 20th of December. His name is Mateo, and there you go with happy smiles. So yeah, luckily my wife held it there for a few more days, and I was able to give you a talk and be with you, and then talk about some science and all this stuff. So about the expansion, and you'll see that photo again for a second, but about the expansion of the universe, it is about 100 years since one of the key papers. Now, it's not the one that you know, and it's not the one that gives the name to the constants. We refer to Hubble, and I'll go into why we call it Hubble. He was wrong, both of them. Lundmark was wrong, Hubble was wrong. Which one was more wrong? So people decided that Lundmark was just a chance coincidence that he got it right, and Hubble deserved the recognition. I'm not going to go into politics. I'm just going to state the fact. But over the years, there's a tension in the Hubble constant, and there's a disagreement of measurements. That's the whole point of the talk. And I've been saying, maybe the Hubble constant is not a constant. And I felt quite isolated there. I felt that people were looking at me like, oh, that crazy guy. The more and more I researched for the talk, the more I realized that actually there are a lot of people like me thinking like that. And not only that, but just 3 days after I decided to give this talk, Phil Plait from Bad Astronomy, you might have seen him in documentaries on Discovery Channel. He's a bald guy with glasses. He wrote a little on his blog. He wrote about the latest result on the Hubble constant. So this is December 9th from the James Webb Telescope, and stated that the Hubble tension is still alive and appears to confirm that the cosmic expansion is different closer to us than farther away, which in other ways means the Hubble constant is not a constant. We know that the expansion of the universe, the rate at which the expansion of the universe is expanding, is not constant. So why would we have a constant all the way from here till the end? It doesn't make sense, but it's very much limited by our capabilities, and that's what the talk is going to be about. This is the Hubble tension. This is the problem. Now you can see that the data is divided, or the results are divided in two parts, one called early, one called late. And at the bottom you have the values of the Hubble constant that they have measured. This part over here at the bottom is a combination of the early versus late. So if you combine all the early data, or what we call early values, and if you combine all the late values and you put them together, how much in disagreement they are. 6 sigma, that's in sigma, this is like essentially saying that it's definitely wrong. Anything beyond 3 sigma is very likely to be different. Anything at 5 sigma is definitely different. If you add 6 sigma, then definitely is. You have more chances to win the lottery than those two values being the same. That's essentially what that says. And we have a different range of values. So what does late means and what does early mean? Because actually quite a little bit misleading in some ways. So if this is the expansion, if this is the universe as it has evolved from the early on through the explosion all the way to recent days, which will be around galaxies on the right. Early means observations when the universe was very young, and late means when the universe is in our neighborhood. So kind of like late means our recent, everything that we see nearby. So in that sense, the light hasn't traveled too much from those sources to us. And here it means that we are pretty much looking at the beginning of the universe. Now, there are no, and this is something that I'm going to emphasize a lot today, and this is really the main reason why I do believe that the Hubble constant could maybe be something in between, like that, not really in between, that it could have an evolution from this value to that value, and it's because we don't have measurements throughout the universe. We have measurements very early, or very early. We have measurements very, very late. We don't have anything in between. So we're assuming that whatever happens here and whatever happens here is the same, is well connected, and nothing has changed. And my belief and my prediction is that this value and this value, I'll talk about that later on, is a weird one. We don't understand it. But if we focus on the 73.3, which is like the typically one that we give from the late, and the 67 that we get from Planck and some other cosmological simulations and measurements, I think we're going to find that there's an evolution of values, 67.4, 68, 69, all the way to 73. And we might have a change in, we will be able to measure how the Hubble constant changed. So we will have a change of the Hubble constant, a period, a H0 dot or something like that, we will have to call it. Now, if that happens, and this is the worry, if that happens, pretty much all the science that I'm doing is wrong. So why do we care so much about the Hubble constant? Because the Hubble constant, as this kind of lambda CDN represents, is part of the cosmological model. It's part of how we, especially when people like me that study objects really, really, really far away in the universe. So I study gamma reversed, in case you need like if you forgot. But I study gamma reversed, and gamma reversed happen across the whole universe. And so I might have one here, and I want to know and measure its true energy output. I want to know how much energy it has produced. To do that, I need to measure its luminosity. To do that, I need the distance. And at that point, I'm going to have to rely on the Hubble constant. So if my Hubble constant is wrong, my values are going to be wrong. Now, one of the issues that we already have is that in the early 2000s, people were doing those calculations assuming a Hubble constant of 73.3. In the 2010s, people started using 70 as a measurement. In the 2020s, people are using 67. And people are comparing results from the early 2000s to the 2020s, and no one has stopped for a second and realized maybe now the true energetics that I'm measuring using different Hubble constants should not be compared. Maybe I should start doing the calculations. Nobody has done that yet. I might ask one of my PhD students to suffer and do that, but we might be getting confused. Like at the end of the day, we might be comparing apples and oranges. And the changes can be quite dramatic, especially if you start going on this region. So the Hubble constant, the farther you go, the more important it will be, as I will show you in a minute. Now, the story of the Hubble constant is the story of saying that we are not, or stating that we are not that special. This is something that I love saying to my students. I always say, I love you, and your parents probably love you, your family loves you, I care about you, but you're insignificant. And I state this: you're insignificant in the whole cosmos point of view. This image, the Ultra Hubble Deep Field, shows us that it's a teeny tiny region in the sky, but it shows us that the amount of galaxies that there are is humongous. We're talking about trillions of trillions of trillions of galaxies. So thinking about us being alone in the universe when there's trillions and trillions of galaxies, even if life is extremely difficult, I'm not talking that aliens will be there, saying hi through the window, but I'm talking about the chances of life existing somewhere in the universe. Well, of course, even if it's extremely rare, with trillions of galaxies, there will be another one. But it wasn't like this view of the universe is extremely new. It's less, actually, about less than 100 years old. Until then, yes, we have Copernicus' model. We even have Kepler's model, with instead of circular orbits, elliptical orbits. But literally, our universe was still the solar system. It was some nebula, some gases out there. It was just our Milky Way. Up to 100 years ago, pretty much. And you will see it on Hubble's result, actually, that they were not thinking of galaxies. We've in the history of humankind, we felt that we were the center of the solar system. We were not. Then we thought, oh, well, we might not be the center of the solar system, but we will definitely be the center of the Milky Way. We're not. Oh, well, the Milky Way is the only galaxy out there. It's not. Oh, well, then this is the only star we have, the only star with the unique solar system. Well, we're not in a unique solar system. There are many other solar systems. Observations constantly show us that we're not that special, and that there are trillions and trillions of galaxies with billions, each of them with billions of suns, and each of them with many, many planets. And once you started doing that, the whole universe is starting to not only to expand, but in the sense of growing, but it also, like the amount of stuff that you had to you had to think and you had to explore, became something, very, very massive. And in 1912, so a little bit more than 100 years ago, we had the first observation that pointed out that there were objects beyond our Milky Way. Now, we call it like this, beyond the first spectral observations of objects beyond the Milky Way, because we know what they are, but Besto didn't call it like that. And what he did is that he measured the spectrum of a few galaxies, and noticed that the absorption lines that show us the composition of the stars and the composition of the galaxy itself, they didn't fall where they were meant to be. They were shifted. Now, the amount of how much they will shift, and actually they were shifted to the red, the amount of shifting that you will get depends on the velocity at which the object is moving. Essentially, the redshift is created by, is defined by an equation like this, where this is the wavelength of the line that you observe. So, and this is the true wavelength, so the true position. So it's the relative position between where you would expect that element to be showing its shadow and where you see it. And as I said, it depends on the speed. The greater the speed, the more the redshift. In this case, much farther. And the redshift actually can be so extreme that it might fall outside your telescope. So imagine that you're observing a galaxy, and with Hubble, eventually, if the galaxy is moving, in this case, or it's really far away, if it's moving really, really fast away from you, the line might eventually fall into the infrared. And that's why, for example, we need James Webb Telescope, because we want to study objects that, from our point of view, they seem to be moving really, really, really fast and away from us. That's what it looks like, but we know that it's not. They are not truly moving away from us. It's the universe expanding and it's making it that way. But essentially, there's a correlation between the speed at which the universe is expanding and the distance, and that's why we just call it redshift to simplify. So that's 1912, and then we have the whole story. We have the whole story in 1922. Friedman use Einstein's equations and say, well, you know what? If you do this with Einstein equations and you do that with Einstein equations, I think the universe could be expanded. That's all Friedman did. Didn't do much. Then Lundmark, using Friedman's ideas, he calculated a Hubble constant that it was 1% wrong from our actual measurement. So 1% wrong. So it was very, very close, but he was using something called galaxy diameters. He used the wrong measurement to Andromeda, because by then we didn't think that Andromeda was a galaxy, and therefore Andromeda had to be a nebula, and the measurement of the distance was completely wrong. So this was very weird. The measurement that he used were wrong. How did he get it right? Nobody knows. But that's why Lundmark doesn't get the recognition that he deserves in that sense. Then 3 years ago, that's 100 years ago. So now that's literally what we are celebrating today in some way. Because he was right. He was right. It's just he had too many wrong assumptions. Then we have Lemaitre, and who, for the first time, created the theoretical framework that we express now like this. The velocity of an object that is moving away from us can be described as the Hubble constant times the distance. So as the distance grows, the velocity at which the object is moving away from us is greater. That's why the redshift, in this case, will be greater. Because if the galaxy is really, really far away from us, that is, if the distance is really great, the velocity will be also really high, and that means you will have much redshift, having to change telescope from Hubble to James Webb. Now, this was the result that Hubble published. His Hubble constant was 500, completely wrong. So I don't know what's worse, of Lundmark's results of Hubble. But look also what he wrote at the bottom there: velocity distance relation among extragalactic nebulae. He didn't even call it galaxy. They were extragalactic, so they were assuming, well, you know what, the distance isn't too far to be part of the Milky Way, but we are the only galaxy out there. These are just nebulae. They are not galaxies. So even Hubble didn't really think of galaxies. I mean, towards the end, yes, but not at the beginning. And definitely, as I said, this slope, which is essentially what measures the Hubble constant, was completely wrong. It was 500, which, remember, we're now closer to a value of 70. So almost a factor of 10. So, to the question, who discovered the expansion of the universe? So, without Lundmark, I don't think Lemaitre would have pushed Friedman's equations and Einstein's equations enough. And definitely Hubble wouldn't have started doing more in-depth observations, I would say. So, he established the first evidence, and then the other two were the ones that provided it. But definitely without Lemaitre, Hubble wouldn't have been able to fit anything to create that slope. So, in some way, we're forgetting one person. So, we established that the universe is expanding. What does it mean? Well, it means that it's growing. But it's not growing in the sense of, that the objects that we were talking up to now, that the galaxies are really moving away from us. It's that the space between us is getting bigger. In some ways, like if you're baking some raisins there, and then the bread just get bigger. The raisins haven't moved really. Some of them might move a little bit, and definitely the farthest objects here, with respect to the center, didn't move at much faster speeds. They're not really moving. It's just the space got bigger. And that's essentially what's happening. It's represented most of the time as a balloon. It's like if I'm doing my business here, I'm moving a little bit. I do have my own motion. You guys are seated, but imagine you have a little bit of motion, and suddenly, after a while, we're just a little bit farther apart. Suddenly the floors have another tile, and another tile, another tile. So we have our own motion. Yes, each galaxy has its own motion. But the space between us, the space is just getting bigger. That's really what the expansion of the universe is. It's growing within. Now, we're not going to talk about what happens if there is an outside to the universe. Why not? But that could be that's a whole different talk. So, because of that expansion, and this is similar to what I showed last year, because of that expansion of the universe, if we study the light coming from a galaxy like Andromeda, what we see is that the light starts in blue, and as the universe expands, the distance is growing, so it's turning redder and redder. And that's because the universe is grown, the wave is attached to the universe, so as I'm stretching it, I'm making the waves farther, like the peaks on the wave of light, they're getting farther apart, so it's getting redder and redder and redder. And that's how we perceive the expansion of the universe, by seeing the light that was originally blue as a red light. There has been a redshift. All the emission that was emitted probably at high energies, now suddenly we see in optical, we see it in infrared. All that emission has been redshifted by the time we get it and by the time we see it. So there's an observational impact on how we see objects due to the expansion of the universe. And the farther they are, the more the impact we get. So, for example, just going to give you something to give you an idea of what happens due to the expansion of the universe. If we had an object that is about the distance of Andromeda Galaxy, as we understand it, 2.5 million light years. I kept it to million light years just for simplicity. I would have used parsec, but hopefully this is better. So we can say that the light has traveled for about 2.5 million light years. That is the clock from the photon as it left the Milky Way, so the Andromeda Galaxy until it got here. It passed 2.5 million, and it's okay. There's no change in there. And we can do that up to 25 million light years, no problem. Now, if we have an object at 250 million light years, that's the distance. So this would be the clock. The clock from the photon that left the object is 250 million light years. But the distance, due to the expansion of the universe, light would have actually traveled 252 million light years. It would have traveled 2 light years more than its clock is actually telling. From our point of view, we see the object as if it was 200 million light years ago, because that's for light. That's the amount of time that it has passed to light. But in terms of journey, in terms of due to the expansion of the universe, considering the size of the universe, the distance really traveled is 252. It's a little bit big. Things are going to get a little more wild if we go, and there's a reason why I go to this redshift. You'll see in a little while. If we go to almost 2,000 million light years, you can see that the difference is getting bigger. That's the expansion of the universe. It has taken so long for that photon to get to us. It has taken almost 2,000 million years to get to us, that by that time the expansion of the universe is noticeable, and it has made it travel about, 137 light years more. If we go to redshift 1, so that's about 8,000 million light years. Now, the difference between the clock on the photons and the actual, sorry for touching the screen, and the actual distance that the photons have traveled is getting even bigger. And if we go to the origin, what we call the origin of the universe, the 13.5 billion light years, that's as far as we can see photons, right? That's we can represent, we can call it as redshift 20. But in that sense, every photon that comes from there has really traveled 33.8 thousand million light years. So the expansion of the universe is quite noticeable, especially when you go really far to Now, of course, there's some assumptions here, and that is, I assume a specific Hubble constant. As I said, if my Hubble constant to convert this into that, if my Hubble constant is wrong, then these assumptions are wrong, these values are wrong, and then everything is different. Why is it important to consider this? Because the brightness of an object decays with the square of the distance. And so it might have been that the photon traveled only for 8,000 million years. The photon has only traveled for that amount of time. Yes, but in terms of the intensity, by the time we see it, it's the intensity of a photon that has traveled for a much larger distance. So we see things fainter because of the expansion of the universe, because in reality, the space has been much bigger. That's very important. That's really critical. If we want to measure the true energy output of an object, we need to consider this. So if we get this conversion wrong, again, we're getting things wrong. So let's measure the expansion and let's show the problems that we have. We need sources that tell us the distance. So let's measure the brightness. Just because an object is brighter, that doesn't mean that it emits more light. I can right now go to Meek and blind him with my torch. I'm not gonna do that. I could blind him. Now, is my torch brighter than that? No. I mean, this is lighting up the whole room. My torch is only blinding Meek. So no, this is emitting much more. But from Meek's point of view, my torch was brighter just because it was closer. Okay, so distance is key. And distance is going to fool it. Is the sun really the brightest object in the sky? No, it's just nearby. Actually, the sun is white. Normal. So that's distance is very, very important. And it's one of the most difficult things to measure. If there's dust in between, if there's dust between me and you, you're going to see me fainter. So you need to measure how much dust there is. But dust is invisible. So how do you know that there is dust? You need to use all the type of telescopes and get a good accuracy measurement. That's actually one of the issues that Lundmark had. The measurement to Andromeda was wrong because our assumptions on we assumed that there was no dust or something. Andromeda was looking a little fainter, and we thought the assumption of dust in between, well, it just was at the wrong distance. So dust can screw up. So you need sources that are less affected by factors that you cannot measure accurately. Otherwise, you're going to start adding what we call systematics. Systematics is when you measure something and you know that there's a factor that is already messing you up a little bit. And you're like, well, I measured 10. But really, because I don't know this thing very well, it could be 8 or it could be 12. So if you can reduce the systematics, your measurements will get better. So what sources do we have? CFITs are fantastic. So CFITs are stars that pulsate. And the beautiful thing that, pulsating in this case really means that they get bigger and they get smaller. So in the stellar evolution, all stellar evolution is a summary of what I call it a delicate dance between gravity, pushing things down, and internal energy, internal pressure, caused by nuclear fusion, pushing things out. If gravity wins, things collapse. If internal pressure wins, things expand. But if things expand and the mass that is inside the star is the same, it means that the way the star carries energy from its core, where everything happens, to the other layers is less effective. If the star contracts, then with all the matter, it suddenly gets more dense, and the energy that goes from the core to the other layers is more effective. It's like, I don't know how many were, but let's say 20, 30. We have our own space. Suddenly the room gets smaller. We all get closer. So we can pass on things, we can chat better. Now suddenly the room gets bigger. We have more room to dance. We have more things to, more space to move. So in CFITs, you have a star that suddenly gets bigger. And when it gets bigger, it gets more luminous, but its temperature decreases. So size and luminosity increases, temperature decreases. When it gets smaller, the opposite. And that happens periodically. And the thing is that because it's a beautiful relationship fundamentally connected to nuclear fusion, there's a relationship between this true energy output, so we call it luminosity, and the period on which this happens. And so if you measure the period, you can measure the brightness. You don't care about anything else. You have a problem with this ones. You just ignore them. But this ones, if you get CFITs, you don't care about, this is the apparent magnitude. This is how we perceive it, right? You don't care about that anymore. You just care about the period. You get the period, you get the luminosity, the brightness. Now, of course, this had to be well calibrated with CFITs where, you didn't have much dust and so on. So that's what gives you the scatter, like maybe some dust that is not very well contained. But if you look at CFITs, and this is what Hubble has done, Hubble, the telescope, and this is what James Webb has done, looking at CFITs in other galaxies, then you don't care if there's intergalactic dust or whatever. You just care about the period. You go here, you say, oh, that's the true energy output. Bingo! I can calculate the distance. If you have the true luminosity and you get how it appears to you, bingo! You can do your stuff. Now, second type, and they got the Nobel for this one, is type 1a supernovae. Why? Because you have a binary system where you have two stars, one evolve a little bit faster than the other one, and it dies. So actually, the primary star is like the sun, not much more massive. So the end up product is a white dwarf. By the end of the lifetime of the sun will not really die with a huge explosion. It would be more like a slow death. And the remnant there is a star that's pure carbon. There's three types. There's the pure carbon, there's the ones that with a little more oxygen, and some that also have a little bit of nitrogen, but they're pure, super dense, about 80% the mass of the sun, something like that, and the size of a planet. So we have that object, has evolved really fast, or a little faster than the other one, and it remains there. Now, the other star that maybe was a little bit less massive, so it takes a little longer for it to evolve, will also evolve into a red giant, and when it gets to a red giant, it's going to start passing some mass into the white dwarf. Now, the white dwarf doesn't like that. And if the white dwarf exceeds 1.4 solar masses, it will go kaboom. But that's the thing. It always happens when it exceeds 1.4 solar masses. So that means that there's a fixed moment in the life of the white dwarf that the white dwarf will die. And all white dwarfs die in the same way. That means that if we measure how the brightness of a white dwarf evolves with time, the peak is always a minus 19. So you just take your supernova 1A observation and you try to match it to get a peak absolute magnitude of minus 19. And to do that, doing that correction gives you the distance. Issue is that you are based that thing into how you perceive the type 1A. So you need to be careful of any possible dust that is making your type 1A a little bit fainter. That could be dust in your galaxy, and that could be dust in the host galaxy, which is much harder. And the farther you go into trying to see type 1As, the harder it is to remove the dust from the host galaxy. So this is a big issue, but it is what it is. Another one that is reporting really interesting results is red giants. The sun will become a red giant. This is the HR diagram where we represent the different types of stars. The sun is a G2, and this is the absolute magnitude or luminosity, so their true energy output. And this is the main sequence. This is where the stars spend most of their life, and depending on their mass, their evolution is slightly different. Cool thing is the stars like the sun will evolve into this RGB, red giant branch, and boom, the tip of the iceberg, where the helium flash. What is the helium flash? Well, the sun will remain here as long as it does nuclear fusion in its core. When it leaves the mean sequence, it means that it cannot produce light by nuclear fusion in its core. It can do it a little bit outside for a little while, but not in its core. The core suddenly becomes dull, becomes dormant. That's why it cools down, because it's not producing as much energy or energy efficient enough. This moment, the helium flash, is a moment where the star suddenly it has now the right conditions to start doing nuclear fusion of helium at the core. And funny enough, that condition is unique for every star similar to the sun. So this happens for every star between 0.4 solar masses to pretty much 4 solar masses, so any star within this range. But the condition for the helium flash, for the helium to go to boom, nuclear fusion, and start fusing, is always the same regardless of the mass of the star, because the conditions for nuclear fusion is they are what they are. There's a physical reason for them to start happening, and it's always the same. And the helium flash, you can actually get the true luminosity of an object at the moment of the helium flash. So all you have to do is try to see that moment. It happens quite fast, so it's not easy to catch a star doing the helium flash or the moment of the peak, but you can do it. And at that moment, more or less its true luminosity. And that's useful. And with that, you can measure the distance. Again, issues with dust and so on, but so far so good. But the thing is that you need to be able to see these objects. And the true brightness of these objects means that you're pretty much limited. Hey, you see now why I put that? So there's that's not May. That should be a million light years anyway. So, but this is called the distance ladder. This is how we, CFITs are more used here. Here we have a combination of CFITs as type 1a supernovae. In fact, actually, sometimes we use the CFITs in other galaxies to calibrate properly the type 1a supernovae, because CFITs are little bit less affected by dust. So based on how we measure its true brightness, and then we try to go a little bit farther out with type 1a supernovae. Definitely the farthest we can go is about redshift 1.5. We cannot see it, and that's because the peak brightness is about minus 19 in absolute magnitude. It means that we don't have the detectability. With James Webb we can improve it now, but it will go to redshift 2, redshift not much. And in redshift, let me see if we can. Yeah, we could probably go to redshift 3, redshift 4. So with Hubble, with James Webb, we have for the first time the possibility of starting to look at this and much farther. Not just for me, this is the local universe. This is okayish, but we really want to go farther out. But it's very difficult, because the farther you go, the less you can measure from. The less you can see from the host galaxies. Actually, sometimes you can barely, or you don't even see the galaxy where the supernova has happened. So how can you remove any contribution of dust from that galaxy if you can't if you cannot really measure it? So that's a problem of bringing this all the way to higher distances. But that has proved, that's how we do it for most of the nearby universe, so the late those, and then we jumped all of a sudden for source 4 to measure. Remember, we were just trying to describe the different ways of measuring the Hubble constants. So the first 3 work only in the local universe, and then suddenly we go to source number 4 and we jump. We barely got it there with the type 1a. Barely got it there to go across the universe, but we are not going across the universe. Now, the cosmic microwave background has gotten, I think it's 3 Nobel winners so far, about 3 different years. The first one was Penzias and Wilson, as I like to say. They got the Nobel for cleaning poop, pigeon poop, to be more specific. Essentially, they had the radio antenna. They saw static all over the place. They cleaned the poop because they thought that there was the pigeons, and there was. The history says that there was a lot. I mean, it was disgusting. And then they cleaned it, and the static was there, and it was uniform. So this white thing that you see is the Milky Way. Sources within the Milky Way that essentially outshines, and they couldn't remove that contribution. This is something that we constantly have to do to get the proper cosmic microwave background. We need to remove any source that is between us and the early universe, and there's a lot of sources. So there's a lot of assumptions, but typically what we do is we remove a little bit more than what probably we need to. So we go conservative. So they got this uniform distribution. There's no fluctuations. Then with COVID, and again Nobel for them, they discovered that that's constant noise that was around 3 Kelvin in temperature, so constant temperature, that pointed to supported the evidence of the Big Bang as the origin of the universe, was not actually 3 Kelvin everywhere. That there were regions with the temperature a little bit higher, and temperature with the regions with the temperature was a little bit cooler. So dark areas is slightly cooler region, bright areas is regions with a slightly brighter temperature. Now, don't get too excited, because if like the the differences in temperature is micro, 10 to the minus 6 Kelvin. So it's just it's minuscule, and that's why it was very hard for them to measure. But the more we try to study these fluctuations, the better we understand, or the better we can build a model of the expansion of the universe, the more we can understand how the universe went from the beginning to what we see now. So, for example, the regions with the warmer regions are a little bit less dense than average. The cooler regions are regions slightly denser than average. If you put clusters of galaxies, you can clearly see that the regions where we had a greater density, it means that there was a little bit more material. It meant that there was more probability to form stars, to form galaxies and groups of galaxies, etc. So in regions of cool regions, that's where we can associate them very easily to nearby local, the universe as we see it now, with plenty of galaxies. And those ones, well, they're still galaxies, but there are not that many galaxies. So we can get a lot of information from those fluctuations. And we've been trying constantly to build a better map of the cosmic microwave background. The best map so far is the one provided by Planck, and is the most accurate. Should we build a new mission for it? I think there's not going to be a mission on the cosmic microwave background at least for another 10 years. Technologically, we need to go even lower than microkelvin for fluctuations. But it's very difficult to go, like this map is like, you just see it as a teeny tiny image, but it's massive. And it's extremely well detailed. Now, there's a few things that we can still try to study. The light, the photons can move like this, the photons can move like that. We call that polarization. And the polarization at the beginning of the universe could be useful to understand part of how the Big Bang happens. And the results are not that great so far. So if you build a newer mission, you can get a better understanding on that. Then there are all the theories that have become more and more attractive. And when I was a student, they were like, nah, and now it's more mainstream. And one of them is the multiverse. And I'm not talking about Marvel Universe multiverse. I'm talking about a universe that is expanding. And next to it, there's another universe that is expanding, completely independent. And then next to it is another universe that is expanding. So that means that there's a greater theme on which the universe does expand. Now, it's a wild theory, but it's getting a lot of momentum and a lot of support. And one of the things that one of these multiverse theories suggests is that we will never detect the graviton. I don't know if you heard of the graviton, but in every force, there's a particle that has that information and carries that information. In light, we have the photons. In other forces, we have their little particles. But in gravity, we don't have a graviton. We don't have a particle that sends the information of gravity, and we can't really quantify gravity at the moment. And one of the ideas is that gravity is not created in our universe. Gravity is felt in our universe, but it comes from a different universe where the graviton is created, hits the surface, the outer layer. Imagine a balloon that is growing, and we are inside the balloon. So the graviton will hit the surface of the balloon, and then it's by that interaction we see gravity as we see it. Now, there's a mathematical, as Roger Penrose said, with math I can create whatever universe. It's the physics that limits me. So there's a limit. We have absolutely no evidence of that. There's a beautiful theory by Lisa Randall on that. You can read her books; they're really, really good. But this is so far a theory. One of the things that it suggests, the way we would see it, if there's a particle hitting our bubble, we should see it here as a pattern like an annulus or something like that. And people have tried to look for annulus in this, and some people have said, "I found it." And someone, and this is not a joke, someone decided to look for Peppa Pig on it. And they found Peppa Pig. And just a way to show that right now, with the accuracy that we get, you can find anything. But maybe they push it a little bit too much. But essentially, so that could be a reason to create a new mission. But they are really expensive. They have very much limited. They have a very limited lifetime. So I would say another 10 years, and then we will see it. But with the microwave background, what we can do, and there's a lot of weird stuff here. So I just wanted to put it there, that essentially, if we cluster all the fluctuations, the cool areas and the warm areas, we put them all together, you can do this kind of graph. And this graph shows in red, the actual values that we get from Planck, and the green line, the solid line that goes around, is our lambda CDM, so our cosmological model. And you can see that the model works really, really well, extremely, extremely well. And this is another reason why there's no need for another. I mean, here maybe we need it, but the model fits so well the data that it's very hard to justify another mission at the moment. And the thing is that from this graph and from this fit, you literally get the Hubble constant. You don't have to do any other assumption. It's just, suddenly you just do the cosmic background, and the cosmic background screams at you, Hubble constant! And this is what it is. So there's little margin of error here. You just measure it. Well, essentially, you do this, and you get your Hubble constant. So while on the other ones, there's a lot of sources of errors, there's very little on this one. And this is why everyone now is jumping into this as the right measurement and not the other ones, because it has less chance.
Sorry, Antonio, could just ask the scale on the bottom, the multiple moment, why is it so different on the left where the error bars are so large? What is that?
It's a log scale. It's a log scale.
Right.
So any errors here, a little bit. It's just, I think it's, the errors get bigger, I think, on the resolution of your... Don't quote me. Is anyone recording this? If I remember well, this has something to do with the size of the fluctuations that you can see. So at some point, you like the size of the measurement of the size of it. You're trying to cluster of the fluctuations, but you have a resolution. The closer you get to your resolution, the worse you can actually measure them, and also you have less. Well, actually, you have even less over here. But those are the big ones, so you can actually measure them very well. I think they're it's close to the resolution of. If I remember well, maybe I'm getting a completely the other one. If I remember well, this is close to the resolution of Planck.
Okay.
So this is why if you build one, you need to focus on improving that. But the model also is a little bit less precise. So the gray area is also where the model fails a little bit. But it works so well that it literally, that's why, like, we all use now 67 because it's difficult to argue with Planck in this case. So, but again, emphasizing, so, and this is also, I don't like this one. And I don't talk too much about that one because this one really takes a lot of assumptions on some theoretical framework on supermassive black holes and other galaxies. So this one is a little more theoretical. This one comes straight from the data. They're consistent, and they're both. So in those cases, they are just a few 100 million years after the Big Bang. So that's why they are both early. But again, even though you can see it, I know it's the word late and it has the word early, but there's a big gap in between. So I was showing before, like this stops at about 2,000 million light years, and this goes to 13.5 million light years, so 13,500 million light years. So there's a difference of about 10,000 million light years where we don't have any observable evidence, or we don't have any measurement to help us bridge that gap. So this is really, rather than late, this is very, very late, so that is very, very local, and this is very, very, very early, and we just don't know what's happening. But all this, including this one, they all have the problem of measuring dust and other assumptions that you have to make sure that your distance is right. It's true that the physics behind the true energy power of the sources, CFITs, type 1As, red giants, is correct. Is that translation between the observation and that where we fail. Now, this is the value from the giant branch. It bridges between the two. Nobody understands why. I'm just gonna leave it there because it's extremely local. This one doesn't go as far as the type 1A. Like the only one so far that's trying to bridge the gap so far as it is the 1A. Hopefully we're changing that over the next decade. But nobody understands this. Maybe the location of the one thing that you need to realize is the location of the stars within the host galaxies. Cepheus, for example, where the ones that we used were always on the outskirts, where you would expect less that. So they are a little bit less affected by that. Giant stars like the sun, they're pretty much in the arms. There are issues. The arms is where star formation is. That means that's where you're going to have a lot of dust, and you're going to have a lot of hydrogen gas, and you're going to have a lot of stuff. Maybe we underestimated, and actually this should be on the 73. I mean, everyone is very happy to see it there, but it's really a little bit meaningless at the moment because it doesn't add into the distance ladder. So we need to bridge the gap. So this is really the last thing, and for today, how do we bridge that gap? So one, there's a new source number 5, which is a combination of gravitational waves and gamma ray bursts. Now, we need both. You could do it with just gravitational waves, but if you look, actually, they didn't do the Hubble constants with the beautiful gravitational wave from 2016, the first. Was it 2016 or 2015? The first black hole merger. Black holes, they emit a lot of gravitational waves, and you can see them farther away. So then, even with the current technology, we can see them farther away than neutron star mergers. But the problem is that you don't know if all the energy went into the gravitational wave, or if there was any other form of radiation, like electromagnetic radiation, that took some of that energy. So in that case, gravitational waves alongside gamma ray bursts gives you both aspects. You can measure how much energy you detect from the gravitational wave and the shape and everything. You know how much energy has gone into light, gamma rays, X-rays, optical, infrared. You put it together, and you can try to measure the Hubble constant. Now, these are different measurements with different assumptions and using different amount of data. So you can see that it differs quite a lot. So you can see this one over here that peaks around almost 80, and you can see this one that agrees perfectly well with blank. So and somewhere and everywhere in between. So it's not very clear. But this was a neutron star merger that happened very nearby. So you would not expect it to fall in here. You would expect it probably more to fall in there. So the fact that we have more curves closer to the 73, I'm okay with it. I'm not angry. This is a very local event. What we need is to change that and to properly bridge the gap. So we need to expand the detectability of gravitational waves. That's going to be done with the Einstein telescope. We can go to redshift 3. Yeah, it's not massive, but we can go now much further and in a very consistent way, better than type 1a. And we're not gonna care. We don't care about any dust, so we are not subject to the same issues. So brilliant, you can actually do it. Now, of course, if you want to do it right, you need to have the gamma ray burst mission that can actually do that. So we're working on Theseus, which hopefully will be selected by 2027, and then will be built by 2030. So will be launched by 2037, 2035. So that's why I said the next decade or two. And putting the two together, we will be able to get, and we've done a lot of simulations on this, and we are going to be able to measure about 50 to 100 gamma ray bursts associated to gravitational waves. And that's key, because if you do that, then you can do 50 to 100 of this. You can do 50 to 100 of this. And that, at the end, gives you an error on the Hubble constant that is less than 1%. That means that your uncertainty in that x-axis, if we were to go back to the tension to here, this error bar would be quite small. It would be so small, would be actually a little bit smaller than the Planck. That's what we want. That way you can actually show this is my error. And now some people are getting more ambitious and they want about 200, because then that way we can split them into distances, slots at different distances. But I think that's beyond the current technology. We would actually be looking at 2050 by then. But I think once we have this 50 to 100 GRVs with gravitational waves with that value, whoever published that paper will get the Nobel. That's my That's because we will go really, really far, much farther than currently is possible without the systematics. And why not? We can add another requirement, which is the use of LISA. Now, LISA is a gravitational wave in space that is going to be launched by ESA. It's currently being developed. And LISA is looking at a different range of gravitational waves. So instead of looking at two objects that are about to merge and crash, it's looking at the merger of supermassive black holes. So the frequency at which LISA operates is completely different. Still, it's so sensitive and so powerful. This is based on a Pathfinder mission that they launched just to prove the technology, and the result was about 100 times better than expected, that we can actually see asymmetries inside of a massive star. Asymmetries inside of a massive star when it's about to collapse, that means that when the star collapses, it can also shake the gravitation, the space-time continuum. It can create gravitational waves. Now, those are too small to be detected by the Einstein telescope, by LIGO or Virgo, but by LISA would be able to do it. And actually, LISA will be able to do it probably a week before the star actually collapses, so we could actually know that it's there. And the other thing is that if it does detect that, it can actually detect them with GRBs at redshift 6 and 10. So we can go, remember, redshift 20 is redshift 20 is the cosmic microwave background. So we would be halfway there for the first time ever. And that, if this person didn't get the Nobel, that person will, because they would be halfway there. So that's what the next 2 decades, maybe 3 decades is that's what we're hoping for the next 2 or 3 decades. And until then, we're not going to have an answer. So if you can ask, what do you believe? I think I stated mine. But, what do you think of the Hubble constant? We don't have an answer, and we will not have it until then. I'm almost certain. And that's it. Thank you very much for listening.